The p block elements, group 15, the nitrogen family. P block elements are present in the rightmost part of the periodic table from group 13 to group 18. Of these elements, there are metals, nonmetals, and metalloids. These elements are nonmetals, these are metals, and in between the two are metalloids. The electronic configuration of p-block elements is ns2np126, that is, their last electron enters the p subshell as shown by red electron. 15th group elements include nitrogen, phosphorus, arsenic, antimony, and bismuth. Their atomic properties: atomic and ionic radii, ionization enthalpy, and electronegativity. Let's first take atomic and ionic radius. It increases down the group due to increase in number of shells. For first two elements, nitrogen and phosphorus, the increase is higher. It is because there is strong shielding effect for s and p electrons. But later on, there is gradual increase due to poor shielding effect of d electrons, that is from arsenic to bismuth. It is from 121 picometer to 148 picometer. Hence, effective nuclear charge increases from arsenic to bismuth. Ionization enthalpy. Due to gradual increase in the atomic size, there is reduced force of attraction between valence electrons and nucleus. Hence, ionization enthalpy decreases from top to bottom. Then electronegativity. There is gradual decrease in electronegativity from top to bottom due to gradual increase in atomic radii. Nitrogen being the most electronegative, having electronegativity of 3.0. Physical properties can be discussed under the heads physical state, metallic character, melting and boiling points, density, and allotropy. The first element, nitrogen, it exists as a diatomic gas, whereas phosphorus, arsenic, antimony, and bismuth exist as solids. Metallic character increases down the group. It is due to increase in atomic or covalent radii top to bottom, which causes a decrease in ionization enthalpy from top to bottom. Hence, nitrogen and phosphorus are nonmetals, arsenic and antimony are metalloids, whereas bismuth is a metal. Melting and boiling points. The trend of melting point is shown in this graph. It first increases up to arsenic and then decreases up to bismuth. The increase is due to increase in molecular mass, but later on, due to loosely packed structure of elements, it decreases for antimony and bismuth. Boiling point of these elements increases down the group due to increase in molecular mass. Then allotropy, that is the existence of an element in different forms. Nitrogen does not show this property, whereas the two main allotropes of phosphorus are white and red phosphorus, and other forms are black and violet phosphorus. Of the true allotropic forms of phosphorus, white phosphorus is monomeric and exists as discrete P4 tetrahedral units, whereas red phosphorus is polymeric. The differences between white and red phosphorus is violet, red, reddish brown, whereas white phosphorus is white or yellow. Red phosphorus is amorphous solid mass, white phosphorus is waxy, translucent, soft. Red phosphorus is odorless and tasteless, whereas white phosphorus has garlic-like taste and odor. Red phosphorus is non-luminescent, whereas white phosphorus is luminescent in dark. Red phosphorus is soluble in carbon disulfide, whereas white phosphorus is insoluble. Red phosphorus is non-toxic, whereas white phosphorus is highly toxic due to its higher reactivity being monomeric. Red phosphorus does not ignite in air, whereas white phosphorus may ignite in air. Having 5 valence electrons, group 15 elements can show both negative and positive oxidation states. They can show -3 oxidation state by gaining electrons, and by sharing electrons also they can show covalency of -3. They can form nitrides like lithium nitride, magnesium nitride, and also calcium nitride. Nitride ion has -3 charge. They can form covalent bonds, show a formal oxidation state of -3 in them also, like calcium phosphide, ammonia, phosphine, and arsine. The oxidation state of -3 has decreased tendency down the group due to decrease in electronegativity down the group. Nitrogen being most electronegative shows maximum tendency to show -3 oxidation state. Then positive oxidation state, +3 being common in all. The stability of +3 oxidation state increases down the group, whereas the stability of +5 oxidation state decreases down the group. It is because of inert pair effect. That is the tendency of a pair of s electrons to remain inert. Bismuth forms only one stable compound in +5 oxidation state, that is bismuth pentafluoride. Like first element of each group, nitrogen also show anomalous behavior due to lack of d orbitals. It has only 4 orbitals available for bonding, that is 1 s orbital and 3 p orbitals, that is 2s and 2 p orbitals. So by giving its lone pair, it can form adduct and show a covalency of 4 as shown in examples. First is NH3 gives electrons to BF3 forming adduct, and next is ammonium ion. NCl5 and NF5 are not known due to lack of d orbitals. Covalency of 5 and sometimes covalency of 6 is also shown. The examples are shown here for phosphorus, arsenic, antimony, and bismuth. Then oxidation state of +5 is shown by covalent compounds, whereas +3 oxidation state forms both ionic and covalent compounds. The covalent character decreases down the group, whereas ionic character increases down the group. Nitrogen has a small size, 70 picometer, has high electronegativity of 3.0, shows strong tendency to form p-pi multiple bond, exhibit various oxidation states from -3 to +5 as shown in different compounds here. A wide range of oxidation states of nitrogen in its compounds. It shows disproportionation reaction due to different oxidation states. All oxidation states from +1 to +4 tend to disproportionate in acid solution. The examples are shown here. HNO2 having +3 oxidation state of nitrogen disproportionates to HNO3, and NO having +5 and +2 oxidation states as shown. Similar is the case for H3PO3. Nitrogen has a triple bond in between the two nitrogen atoms, which is a p-pi bond. Two bonds are pi bonds, whereas one bond is a sigma bond. The ground state electronic configuration of nitrogen, ground state electronic configuration of another nitrogen, showing the bond formation p pi bonds between last two p orbitals. Then chemical reactivity towards hydrogen. These elements combine with hydrogen to form hydride of formula EH3. The examples are shown here. With hydrogen, nitrogen forms ammonia, phosphorus forms phosphine, arsenic forms arsine, and so on. Gradation in chemical reactivity. The stability of hydrides, it decreases down the group due to increase in size of the element. Bond dissociation enthalpy also decreases down the group. Hence, bismuth hydride is strongest reducing agent as the bond is broken easily and it is thermally unstable. Basic character. All these hydrides are basic in nature as shown by the litmus paper. It turns red litmus to blue. Order of basicity. Ammonia is most basic amongst all and decreases down the group basicity. Gradation in chemical reactivity. Boiling point. It first decreases from ammonia to phosphine and then again increases due to increase in molecular mass. Ammonia has higher boiling point due to presence of hydrogen bonding. Then chemical reactivity towards oxygen. It forms different oxides, and as the number of oxygen increases in these oxides, the acidic strength increases. Acidic character of oxides decreases down the group. Here are the resonating structures of different oxides of nitrogen. Some of these dimerize due to presence of odd electron, like NO2 dimerize to form N2O4. Then chemical reactivity towards halogen. With halogen, it can form two types of halides of formula EX3 and EX5. The examples are shown. These elements can form PX5, AX5, ASX5, SBX5 antimony pentahalide. Nitrogen cannot form pentahalide as told earlier due to absence of vacant d orbitals. The covalent character of these halides decreases down the group. Here are the halides of phosphorus, phosphorus trichloride and phosphorus pentachloride. Phosphorus trichloride is trigonal pyramidal, whereas phosphorus pentachloride is trigonal bipyramidal. Then uses of dinitrogen. Due to presence of triple bond, it is used as an inert atmosphere in iron, steel and other metallurgical industries, prevents the formation of undesirable oxides, prevents the harmful effects of oxygen, dilutes the activity of oxygen, preservation of packaged food materials, application in the manufacture of fertilizers, a refrigerant to preserve biological material. It is also used in cryosurgery to remove warts and other skin lesions. Then an important compound of nitrogen, that is ammonia. It is commercially formed by Haber's process, which uses iron oxide as catalyst with alumina and pressure of 200 to 300 atmosphere at 700 Kelvin to increase the rate of reaction, though the reaction is exothermic. Here's the flow chart for formation of ammonia through Haber's process. Then some properties of ammonia. It's a colorless gas with pungent smell. Boiling and freezing points are given. Then hydrogen bonding is there. Liquid and solid state both exist. High heat of vaporization, highly soluble in water. Aqueous solution of ammonia is alkaline, that is basic in nature. Dissociation constant very small, that is a weak base. Acts as a Lewis base as it can donate its lone pair of electrons. Precipitates hydroxides of metals from their aqueous salt solutions. A complex is shown due to its ability to give its lone pair of electrons. Then commercial scale preparation of nitric acid, another important compound of nitrogen. It is by Ostwald process. First step is catalytic oxidation of ammonia into nitric oxide. Then nitric oxide is oxidized to nitrogen dioxide, and then nitrogen dioxide to nitric acid. Here's the flow chart for Ostwald process. Then some properties of nitric acid. It reacts with metals. Dilute acid and conc acid give different products. With concentrated nitric acid, copper and zinc gives copper nitrate and NO2 gas. Whereas with dilute acid, copper gives copper nitrate and nitric oxide, and in case of zinc, it is N2O. Then properties of nitric acid. It's a strong acid. Hot and concentrated nitric acid is a powerful oxidizing agent. It can dissolve copper and zinc as shown here, but noble metals are insoluble in it, though they can be made soluble in aqua regia, which is a combination of nitric acid and hydrochloric acid in the ratio of 1:3. It is due to formation of nascent chlorine that aqua regia is able to dissolve noble metals. Then it also reacts with non-metals. With carbon, it forms carbonic acid. With phosphorus, it forms phosphoric acid. With sulfur, it forms sulfuric acid. And with iodine, it forms iodic acid, as it can give nascent oxygen. Then the Brown ring test, which is an important test of practicals also. The Brown complex is formed when nitrate ion is treated with ferrous sulfate solution and concentrated sulfuric acid. The Brown ring is formed at the junction of two solutions. The complex formula is given here. Then some uses of nitric acid. It is used in the manufacture of dyes and drugs and explosives like TNT, nitroglycerin and picric acid. Then some fertilizers, ammonium nitrate and calcium nitrate. Then purification of silver and gold. Also used in laboratory as oxidizing and nitrating reagent. Then pickling of stainless steel, etching of metals and oxidizer in rocket fuels. That's all. Thank you.